Welcome to the online course on pericyclic reactions and organic photochemistry. We are in module 33 now. This is the module concerning the photochemistry of aromatic compounds. Aromatic compounds are pi electron rich compounds, so their photochemistry is rich in pi star excitation processes. If you take benzene itself, it has absorption in the range of 180 to 200 nanometer one set of bands, 200 to 220 another set of bands, from 220 to 250 another set of bands. All of them are pi star excitation band corresponding to electronic excitation going from S0 to S1 and S2 states. As the wavelength decreases, the energy increases corresponding to the excitation. The primary photochemical process of benzene and its derivatives can be classified as follows. From the first excited singlet state, which is a pi star state, one can expect intermediates which are zwitterionic in nature, and the zwitterionic intermediates, once they are formed, it goes to the final product. There is a definite evidence for the involvement of zwitterionic intermediate, which are done by trapping experiment. The first excited singlet state, which is a pi star excited state, can also go through a funnel mechanism, which is a concerted mechanism to go to the product without the involvement of any kind of intermediate. Finally, a triplet excited state, pi star state, can also go through an intermediate stage, which is a diradical state, resulting in the product formation. We will see examples of each one of these cases in the coming slides. So this is a schematic representation of what is said in terms of the schemes here. The S0 state is essentially the ground state benzene state, which is the canonical structures are written here. The first excited zwitterionic state is essentially 1,3 dipole kind of a state, or 1,2 dipole kind of a state, as indicated here. These are all resonance structures of each other. And the triplet state is a biradical state. Biradical state is also represented as either 1,3 biradical state or 1,2 biradical state, and so on. The reason this kind of a bridged bicyclic system diradical state is given, there are products which are arising out of the biradical intermediates of this type as well as zwitterionic intermediates of this type, which we will see in the due course of this particular module. Now, whenever you have a strongly electron withdrawing functional group like the nitro functional group, cyano functional group, ester functional group, and so on, the zwitterionic intermediate is favored in this manner such that the anionic charge is close to the electron withdrawing functional group. This is understandable because the anionic charge will be stabilized by the electron withdrawing functional group by delocalization process. Similarly, when there is a strong electron donating group like the methoxy group or the amino functional group, it is the cation of the zwitterion is close to the electron donating functional group because the electron donating functional group can stabilize the cationic charge by delocalization process. And there is again evidence to show that this kind of zwitterionic intermediates are formed during the course of the photochemical reactions of benzene derivatives. Now let us go into the various types of reactions that benzene can undergo. When benzene is photolyzed in less than 200 nanometer region, which is the vacuum ultraviolet region, for example, this would essentially correspond to excitation from S0 state to S2 state. So the resulting photochemistry actually could be arising from the S2 state in this particular case. A mixture of compounds are formed. All of them are isomers of benzene, for example. This is dimerbenzene, this is benzoylene, and this is fulvalene. These three products can be formed in this particular reaction. On the other hand, a bridged cyclophenic kind of a system, when it undergoes the photolysis under this condition, it is only the dimerbenzene that is formed because of the constraint of the bridge that allows the formation of only the dimerbenzene. None of the benzoylene or the fulvalene product can be formed under this condition. Another example of dimerbenzene formation is a highly substituted molecule. This is a hexafluorobenzene. Hexafluorobenzene is an electron deficient benzene system compared to benzene itself because of the electronegative fluorine that are attached to it. Nevertheless, it undergoes the UV radiation nicely to give the dimerbenzene as the product. Heavily substituted benzenes, which are substituted with tertiary butyl groups, which are sterically hindered, for example, this ortho ditertiary butyl group is sterically hindering each other. So the molecule is not definitely planar in this kind of a system. So in order to relieve the steric hindrance, it undergoes the reaction to give the dimerbenzene. In the dimerbenzene, of course, these two tertiary butyl groups are going to be farther away. This is going to be in the plane of the double bond, whereas this is going to be above the plane of the double bond, for example. So these two tertiary butyl groups will move away from each other during the course of this reaction. This could be one of the driving force for this reaction. Benzene itself undergoes this reaction only at a very low wavelength. In other words, high energy radiation is necessary, whereas this reaction can be performed by irradiating the benzene around 250 nanometer itself, indicating that this could be arising actually from the S1 state of the benzene. Again, heavily substituted naphthalene or anthracene units can also undergo the electrocyclization, intramolecular electrocyclization reaction to give the dimerbenzene. Here again, intramolecular electrocyclization reaction gives the dimerbenzene as the final product in this particular case. The mechanism of formation of these various products that we have seen in the case of benzene is shown here. When it is less than 254 nanometer, this could be arising out of the S2 excited state of benzene, giving the dimerbenzene. If it is arising from the S1 excited state of benzene, then you can invoke a dipolar state of this kind. From the dipolar state, for example, one can easily go to the benzvaline by connecting this carbon and this carbon with a double bond here, or connecting this carbon and this carbon with a double bond resulting here, essentially forming the benzvaline. The reason that it is possibly a zwitterionic intermediate is given by the trapping experiment. When methanol D is used, for example, the methoxy group essentially goes to the cationic part and the deuteron go to the negative part in kind of producing this particular molecule. Fulvaline can also be explained by the ring opening of this cyclopropyl ring that is shown here by means of a breaking of either this bond or this bond, followed by the rearrangement of the pi electron system to give the fulvaline as the final product in this particular instance. Now, certain substituted benzene derivative, particularly mesitylene and trideuterobenzene 1,3,5-ditetrobenzene, when it is photolyzed, they undergo the transposition of the substituents by scrambling of the substituent, for example. This is easily explained by the formation of benzvaline as the intermediate. The benzvaline is essentially formed by the mechanism that is shown by this arrow. This is a 1,2 shift followed by a 1,2 shift, resulting in the formation of the two blue bonds are formed during the course of this reaction. And when you break the molecule to go to this particular product, the two red bonds are to be broken, and that will essentially give the, this is a 1,3,5 substituted starting material, which gives 1,2,4 substituted derivative during the course of photoisomerization, which transpositions the substituents in a different manner compared to the starting material. The mechanism essentially involves an intermediate which is a benzvaline intermediate. The benzvaline intermediate can reversibly undergo this particular, here also the reversible arrow should be there. In fact, it can reach a photodynamic process. In other words, the photostationary state can be obtained by this particular reaction. The concentration of the individual species will depend on which one is absorbing and which one is facile in terms of undergoing this benzvaline structure and so on. Now, further examples of electrocyclization involving heteroatom in this case, for example, this is diphenylamine or diphenyl ether or diphenyl sulfide. A 6-electron cyclization can take place. 6-electron cyclization will form a bond between these two centers. Why 6 electron? 2 electrons from this benzene, 2 electrons from this benzene, and a lone pair of electron from the heteroatom. So overall it is a 6-electron system. Under photochemical condition, it is a conrotatory process resulting in the formation of a dihydroaromatic derivative, which is oxidized by either iodine or oxygen to give the fully aromatic. It can give either this can give dibenzofuran, dibenzothiophenone, or dibenzopyrrole, for example, as the case be. Dibenzopyrrole is essentially when X is equal to NH, that will be dibenzopyrrole. Now, this molecule essentially is undergoing electrocyclization reaction followed by a hydrogen transfer to this position, leading to the formation of this trans stereochemistry in this particular junction. The mechanism is when the alpha beta unsaturated ketone is part of the ring system. Mechanism involves a zwitterionic species here. This is essentially an electrocyclization followed by proton transfer to give this particular product. The dipymethane rearrangement is possible. We have already seen this in the dipymethane system. Let me recap it. Dipymethane rearrangement is nothing but 1,4-pentadiene kind of a derivatives, where 1,4-pentadiene is part of an aromatic system, resulting in the formation of a cyclopropyl phenyl derivative is the dipymethane rearrangement. In other words, it is a 1-2 shift is what we are talking about in terms of the rearrangement process. This is essentially happening in the presence of a sensitizer. That means it will undergo this reaction through a triplet state intermediate is what is formed in this particular case. So all these cases essentially correspond to the dipymethane rearranged product. Here dipymethane rearrangement can give potentially two products. The double bond can be either here or here in the canonical structure. So the two types of products that are indicated are given in these particular structures of the product that are shown here. Now photodimerization of anthracene is something we have dealt with in the pericyclic reaction. Photodimerization of anthracene essentially involves the 9-10 position of anthracene, resulting in the formation of photodimers. This is a head-to-tail dimer and this is a head-to-head dimer. Depending upon the orientation of the two anthracene unit, one can either form the head-to-head or head-to-tail. In fact, both the compounds are formed as a mixture in most of the photochemical cycloaddition of anthracene. Naphthalene can also undergo the 4-pi cycloaddition reaction. Essentially, it can either overlap on top of other or it can overlap by sliding itself into the other ring, sliding out of the plane of the methoxy ring, resulting in the formation of two types of products. Both the products are essentially 4-pi cycloaddition product, which could be a concerted process arising out of the funnel mechanism. In other words, this is probably no intermediate is involved. The first excited singlet state essentially directly undergoes reaction with the ground state anthracene to produce this molecule through a funnel mechanism, which is essentially a Frank-Condon transition is what is taking place during the course of this reaction. Benzene does not undergo Diels-Alder reaction except with dicyanoacetylene. With acrylonitrile or electron rich or electron deficient olefins, it undergoes 2+2 cycloaddition reaction, which could be considered as a concerted reaction. The 2+2 cycloaddition reaction essentially is a stereoselective reaction. The formation of this particular product in 5:1 ratio is what is the diastereoisomeric products are arising out of 2+2 orthocycloaddition. Here electron rich olefin also undergoes 2+2 cycloaddition reaction to give the corresponding benz-cyclobutane product. This is not benz-cyclobutane, it is cyclohexadiene fused with the cyclobutane as the ring system that we have in the product stage. The reaction has been shown to be stereospecific when cis and trans isomers of 2-butene are used. When cis isomer of 2-butene is photolyzed along with benzene, the corresponding 2+2 cycloaddition reaction product is formed with the two methyl groups which are cis with respect to each other. So essentially it's a highly stereospecific reaction. When the trans isomer is used, the cyclobutene with the two methyl groups are formed with the trans stereochemistry with respect to each other. These three products which are arising out of 2+3 meta-cycloaddition product, we will discuss it in the next slide. Now in the case of these three products which are separately written here, with cis-2-butene and trans-2-butene, the two products are formed. If you trace out the red portion of the molecule here, you will see benzene. In other words, this is 1, 2, 3, 4, 5, 6. So this corresponds to a benzene ring. Obviously, the addition has undergone 2-3. In other words, the 1-3 position of benzene has undergone cycloaddition reaction with the olefin. So overall, if you look at it, it is looking like a 3 carbons of the benzene and 2 carbons of the olefin are undergoing the cycloaddition reaction with a concomitant rearrangement of the pi system to give this particular product. The mechanism can be explained as follows, with the cyclopentene as illustrating the example. Cyclopentene undergoes 2-3 cycloaddition process to give a diradical intermediate of this type. The diradical can either close from here to here or it can close from here to here. These are the two processes that can be shown. And obviously the two products that are formed are this product and this product. These two structures are identical structures. If you want, you can number the structures and follow the numbering to arrive at this structure. So essentially this structure is formed by 1-3 ring closure of these two radical centers. 1-3 ring closure of these two radical center will essentially form this particular product in this particular case. So the formation of these three products can be explained on the basis of the 2+3 meta-cycloaddition process. It is a very interesting reaction. You can see here it's a highly strained molecule. A tricyclic molecule is easily produced from benzene by photolysis with a simple olefinic kind of a system. Now the fact that we are invoking a diradical intermediate needs proof as far as the mechanistic detail is concerned. When the SO compound of this kind is decomposed, either this SO compound or this SO compound is decomposed, it forms the diradical intermediate. The SO compound decomposition also gives the same product as the benzene cycloaddition product. These two products that are formed here, these three products that are formed here, can essentially come from the decomposition of the SO compounds also, indicating that the diradical intermediate is a true picture of the mechanism of this particular reaction of 2+3 cycloaddition process. When highly polar substituents are there, either electron donating substituent or electron withdrawing substituent, it's possible that this reaction goes through a dipolar intermediate. The dipolar intermediate is shown here, for example, 2+3 cycloaddition reaction of benzene. In the case of the methoxy substituted derivative, will have this particular system. Now this can undergo ring closure between these two carbons or between these two carbons, essentially forming this particular product. In the case of electron withdrawing substituted derivative, the negative charge stays with the cyano-functional group. Again, the bond formation between these two centers will produce this particular product. Between these two centers will produce the other product, which is this particular product, for example. So one can invoke the formation of the zwitterionic intermediates of this type in the 2+3 cycloaddition process, particularly with the electron rich as well as electron poor benzene derivative. The possibility of these intermediates do exist, which can be explained by the stabilization of the charges by the electron donating and electron withdrawing substituents in these systems. So without any electronically biasing substituent, it can go through a diradical intermediate of this type. With strongly electron influencing systems like the electron donating or electron withdrawing substituent, it could be a zwitterionic intermediate of this type. Synthetic applications of the metacycloaddition is what is given here beautifully. These are intramolecular versions of the cycloaddition reaction, so it gives a fairly complex tetracyclic compound of this type. Essentially, the cycloaddition reaction takes place between the 1,3 positions, which are indicated by arrow across this double bond, resulting in the formation of this structure. So if you follow the black portion of the substituent, essentially that will give you the pendant group. The red portion essentially indicates the benzene ring itself, which has undergone substantial reorganization in terms of the metacycloaddition process. Again, you will see that the metacycloaddition process is a highly stereoselective process. The stereochemistry of the double bond is essentially retained in the product also. As you can see in the stereochemistry, this is hydrogen and methyl are trans. You can see hydrogen and methyl are trans. Here the hydrogen and methyl are cis. Again, the hydrogen and methyl are cis in this particular product of cycloaddition product that is shown here. The synthetic application of metacycloaddition is further illustrated by the addition of this pendant group, which is attached to the benzene ring, in terms of forming the angularly fused system as well as linearly fused system. The angularly fused system is further transformed into a terpenoid molecule, namely sulfinene is the terpenoid molecule. A racemic mixture of the racemic synthesis of the sulfinene is essentially made from this angularly fused 2+3 cycloaddition product of this pendant group to the benzene unit, which can be traced by the color coded ring system that are here. This is part of the originally the benzene ring. This is also part of the original benzene ring. The substituent, which is this one, is given in the black portion, so one can easily trace out the cycloaddition process as 2,3 cycloaddition process. Let us look at some beta cleavage processes, which are homolytic cleavages. If you take, for example, phenyl acetate, which is a starting material, when you photolyze the pi star excited state of the phenyl acetate, essentially weakens the beta bond, which is this particular bond. This is alpha bond and this is beta bond, producing acetyl radical and phenoxy radical. The acetyl radical recombines in the para position as well as in the ortho position, resulting in the formation of the corresponding intermediate biradical stage. The intermediate biradical recombination in the ortho and para position will give this intermediate, which is undergoing enolization to give the phenolic product, which is the orthohydroxyacetophenone and parahydroxyacetophenone as the product. This reaction is known as the photofreeze rearrangement because it resembles the freeze rearrangement, which is triggered by Lewis acid catalyzed rearrangement of the phenyl acetate, for example, to give the same class of products that is shown here. These are photofreeze-like rearrangement. The corresponding amino derivative, which is the amide acetanilide, for example, on photolysis gives you orthoaminoacetophenone and para-aminoacetophenone, and a small amount of aniline is found because of the leakage of the acetyl radical from the reaction medium. This is another example which is photoclaison rearrangement. Essentially an allyl radical and phenoxy radical is produced. The allyl radical combines in the ortho and para positions to give the ortho allyl phenol and para allyl phenol. Phenol is also a byproduct that is formed in this particular reaction. Now let us move on to nucleophilic aromatic substitutions by photochemical reaction. These reactions are normally not possible under thermal condition. For example, if we take metamethoxy nitrobenzene and treat it with sodium hydroxide, under thermal condition no reaction can be observed. However, under photochemical condition, the substitution of the methoxy group, which is normally not a good leaving group, takes place, producing the metanitrophenol, for example. Similarly, if you take 3,4-dimethoxy nitrobenzene, it is specifically the metamethoxy with respect to the nitro, that methoxy alone is substituted. If you similarly take the 2,5-dimethoxy nitrobenzene, it is the metamethoxy with respect to the nitro is specifically substituted. So the reactions are highly regiospecific in nature. At least these two examples seem to tell us that the group that is meta to the nitro group is what is substituted. So it is highly regiospecific in nature, which can be explained on the basis of formation of this kind of an intermediate. Remember, the zwitterionic intermediate is the S1 pi star state is the zwitterionic intermediate. In fact, we are doing an S1 pi star excitation of this aromatic unit is what we are doing here. Once the zwitterion intermediate is formed, it is easy to see why the nucleophile will attack in this position, because it is an electron deficient position. The anionic charge is stabilized by the nitro functional group, whereas the cationic charge is stabilized by the methoxy functional group. So nucleophile can essentially attack this position with the methoxy as the leaving group, for example, which would explain the formation of the products that are shown here. Alternatively, if you have a good leaving group, which is a halogen as a leaving group, for example, and if you have a very powerful nucleophile, which are carbon nucleophile, one can also have a mechanism passing through a radical chain mechanism. Let me explain this mechanism. Initially, the benzene ring is substituted with a leaving group, which could be a halogen like chlorine or bromine or iodine. Upon photolysis, it goes to the singlet excited pi star state, and under this condition, a powerful nucleophile like a carbon nucleophile can undergo electron transfer process to the excited state molecule, resulting in the formation of an anion radical, and the nucleophile radical also will be produced in the process. In other words, there is an electron transfer from the nucleophile to the excited state of the benzene ring, producing the anion radical of the benzene ring itself. Now, this is a fragmentative process. Once the anion radical with the chlorobenzene anion radical is formed, the carbon-chlorine bond can be easily cleaved. Chloride can leave, for example, producing a phenyl radical. The phenyl radical can be trapped by the nucleophile to give another radical anion species, which is a chain propagator, for example. Now the starting material can be reduced. In fact, the reduction potential of this should be lower than the reduction potential of this. So electron transfer can take place between these two, producing the chain propagator and the nucleophile substituted molecule. These examples of this kind of reaction is illustrated here. Typically, these reactions are carried out in a very polar solvent like ammonia or DMSO and so on, where the anions can be easily generated. In this particular instance, for example, acetonitrile anion, which can be generated from acetonitrile in ammonia or in LDA as the base, for example, the paraphenyl substituted biphenyl 4-chlorobiphenyl, for example, undergoes substitution by this carbon to give the corresponding CH2CN substituted product. In this case, this is acetylacetone is the molecule. Acetylacetone can produce the corresponding carbanion in the presence of ammonia, and the carbanion essentially undergoes the substitution of the bromine via this radical anion mechanism through electron transfer process. So these are called the substitution nucleophilic radical aromatic aromatic substitution reaction is what we are talking about. Radical mechanism is what we are implying in this particular case. In this case, there is a selectivity between bromine and iodine. Iodine is specifically substituted by acetophenone anion, for example, to give the corresponding benzyl phenyl ketone as the final product in this case. What we have seen is a glimpse of the photochemistry of aromatic molecule, which are rich in pi star excited state process. The models for the pi star excited state depends on whether we are dealing with the first excited state singlet or first triplet excited state of the molecule. The first excited singlet state is typically a zwitterionic kind of a intermediate, whereas the first triplet state is a biradical kind of an intermediate. The various reactions arising out of the benzene transforming into 2 plus 2 cycloaddition reaction or 2 plus 3 cycloaddition reaction or substitution reaction can be explained by invoking the Zwitter ionic intermediate or the diradical intermediate kind of a model systems that we discussed. I hope you enjoyed this module. Thank you very much for your kind attention.